So just a couple of notes before I get started. So with regards to the last homework, the last homework we have so we have one last homework. Oh, sorry, we have three last homeworks, right? We have the sorting. Sorting you should have received an email that is now extra credit. Doing it means it's 30 points of extra credit. So it'd be 30 points out of 0, right? Which means that gets added, that's 30 points, about a third of an assignment that gets added to your final grade. And yes, it's possible for your assignment. And if you end up getting, slightly more, like if you end up with like, say there's 1,000 points, let's say there's 1,000 points and you've been doing extra credit and you end up with like 1,050, that does mean you'd earn more than 25 points from the assignments. So it does overflow, so to speak. So the remaining 2 assignments, it's really 1.5 assignments. Okay. What we have here is that we have the graph homework, right? We have the graph homework. And then we have the security homework, right? Security homework. All right, the graph homework is worth 50 points out of 50. And the security problem, from Project Euler, is worth 100 points. Okay. The point of the graph assignment is to make sure that you're ready to do the security problem. Okay. This is part of the reason why I said you can use any language for it, because pretty much no programming language has a built-in graph library. I assume everybody can hear me. I never actually double checked. Can everybody hear me?
Yeah, we can hear you.
Great. Okay. So the graph homework that you need to do, it's very simple. You implement breadth first search and depth first search. Breadth first search is fairly easy because you use a queue to do so. And the stack's a bit trickier. Follow the pseudocode. You can do it either recursively or iteratively. The main thing is that for a stack and the queue, what you need to make sure you do is that you have a set. You use a set, right? A set to keep track of what you have visited, right? You keep track of the nodes you have visited so that you don't end up in an infinite loop. Okay. If you're going to do the graph homework, basically you'll either want to follow the directions for Jung, and basically the entire point of that 50-point assignment is just to make sure that you've got Jung working. Okay. And I have videos on showing how to install it on Eclipse, on IntelliJ, and on that third one, NetBeans, that I've not seen any students use, thankfully. Okay. If you, on the other hand, are brave and are deciding to do this in Python, you want to do network. You want to pip install network X. And that's fairly intuitive on how that works. You can turn you create a graph and you can make anything be nodes and you can make anything be edges. It's very useful. For the security assignment, which is the last assignment, if you've been doing the rest of them, I believe I drop one assignment. So you could ostensibly just not do that. But for the security assignment, that is actually a topological sorting algorithm in disguise. Okay. So here's what you want to do for that. You want to use something called Kahn's algorithm, right? Kahn's algorithm. Make sense? Look it up on Wikipedia. It's a very, very nice and clean algorithm, and you can even simplify it for this assignment. Okay. You can even simplify it for this assignment. I'll try to talk to Kenichi to have him go over that in lab on how you do that, so I don't take up too much review time going over it. But Kahn's algorithm is what you do for this. It's a very straightforward kind of assignment to do the homework. Once you do that, the hardest part is actually loading in all the nodes and populating your graph. But basically that security problem is just a graph problem in disguise. And that's it. All right. So with regards to the final exam, I believe Professor Dobor is creating the final exam mainly because, but I think he's using the last year's exam, which I wrote as a basis. So, or last semester's. So I will double check with that to make sure. But generally the way this works out is that it's 50-50 on theory and practice. And I never bothered writing a practice exam for the final exam because I'm lazy. And instead, what we're going to do is I'm going to go ahead and go over Harvard's final exam instead, because I found it works pretty well. It has a lot of good questions that I really like on here, and a lot of good theory and practice questions. And then I have a bunch of other questions from other final exams that I've scoured over the years that have been very good. Okay, so we'll go ahead and just jump right into it. Okay. And the final is cumulative, so it goes over everything, except for the topological sorting. What you're going to need for graphs is three things. You need to know how to do breadth first search, depth first search, and then you got to know Dijkstra's. Doesn't matter what computer science course you take. If you learn graphs, you learn Dijkstra's. Doesn't matter if you've learned it a million times already, you're going to learn Dijkstra's again. Okay? Make sense? And whenever you learn Dijkstra's, it's going to be on an exam. I took a networking class, and the shortest routing algorithm was Dijkstra's. So I had to learn Dijkstra's again for that class and do it in the exam. And let me tell you, that was fairly straightforward. Once you know it, learned it once, it's fairly easy to remember how to do it. Okay. The hardest part about spelling Dijkstra's, once you've learned it, will be how to spell the name. Okay, the hardest part about learning Dijkstra's is just how to spell the name. Okay. When will exam 2 be graded? That is a good question. I've lost a week. I told Kenichi to grade them. I am going to go ahead and let me go ahead and put a reminder after this class that I will immediately get in contact with Kenichi, because I've literally not been able to go to campus. It's been a rather difficult week for me. Okay. Just writing this down to go so I don't forget. Okay. Okay. All right. So, and again, if you have any issues with the way exam 2 ends up being graded, please let me know. All right, let's suppose that items A, B, C, and D, and E are pushed in that order onto an initially empty stack. Let's see. So why did I close the whiteboard? Silly me. Let's see. And I can just exit Steam for right now, because I don't need to see notifications about what random friends I've had in college are playing. Okay, so go back to this. Okay, so A, B, C, D, and E are pushed onto an initially empty stack. Sorry, 1 second. I didn't mean to do that. Okay. So we've got A, B, C, D, E pushed onto initially empty stack. When we're dealing with graphs and stuff, with stacks and stuff like that, and all these data structures, always write write your work down. All right. S is then popped 4 times. As each item is popped off, it is entered into an initially empty queue. So the first 4 items will go adios. So, and then they'll get into a queue. Right? E, D, C, B. If 2 items are then removed from the queue, what is the next item that would be removed? Right? So A, B, C, D, E are added on. We pop 4 of the items off and put them into a queue. Because the way a stack works, E is at the top of the stack, so that goes in first. So we end up with E, then D, then C, then B. Remember, so it's a first in, first out for Q, whereas it's first in, last out for a stack. So the answer is C over here. All right, next one. If the binary tree below is printed in pre-order traversal, what will the result be? All right. So pre-order traversal means that we do the root, then we do the left subtree, then the right subtree. So A and B are wrong right off the bat because they start off with 9. 9 would be the correct starting point for a post-order traversal. Pre-order means we start at 6, okay? And then we want to process the left subtree. So C's out. So we go to 17. And then so we do the left subtree. To do the left subtree, we process 17, then we process the left subtree, then the right subtree. So it would be 6, then 17, 9, 4, and then 22, 16, 12, which is so 6, 17, 9. So the answer is E. Everybody following so far? I'm going to be basically just hitting the ground running with this because I do want to give you as much. Is this PDF available for on campus? On Canvas? I used to have a PDF for everybody to look at, but guess what? I'll just simply drop this on the chat so that you can look at it. Okay, there you go. There it is. There's on chat. All right. So a graph implementation that uses a two-dimensional array to represent the edges would be most reasonable for the following cases. 1,000 node, 1,200 edges, 100 nodes, 4,000 edges, 1,000 node, 10,000 edges, 10 nodes, 20 edges. E, none of these, since a graph can only be represented as a linked structure. Now, you may think you haven't learned this yet, but we have. We did learn this, and we did go over this in the graph videos. So graphs can be represented in one of two ways, right? Just to refresh your memory, or in case you did not watch the videos. Graphs can be represented in one of two ways. Graphs can be represented as either a linked data structure, where basically what we do is that for every node, in that case, right, what do? We have like we would say, okay, node A connects to node B, and it also connects to node C and D, and B connects to A and F, right? And C connects to A, and so on and so forth. Right? We'd basically list what our connections are out with. That's the linked data structure. The other way of doing that is basically having a array. A, B, C, wow, really bad today. A, B, C, D, E, right? And then A, B, C, D, right? And basically, depending on how it works, right, you basically say this is the source and this is the destination. So there's a directed edge from A to B, and it either exists, or maybe we can write, or you can also use numbers to say like it's a directed edge of a weight of 3. Basically, there's two ways of doing it. You can have a graph, so you can have this two-dimensional array, and you can have this linked data structure. Which is better? And the answer is it depends on the context, just like linked lists and array lists. In this case, a linked data structure is better on a sparse graph. Okay, meaning that there aren't that many edges. What does that mean? And then this one and this one, if it's good on a one without many edges, then the array list should be the one that's good on dense graphs, the one with a lot of edges. Okay, what does this mean? That means that if we have V vertices, right? If we have V vertices, okay? If we have V vertices, that means that the max number of edges you can have in a simple graph. Okay, what's a simple graph? A simple graph is graphs data structures. So graphs come in two. We only deal with simple graphs in this class and pretty much in every other class. A simple graph is exactly what you'd expect. Basically, you have nodes and you have edges like that. That's a simple graph. The other option is having a multi-graph, which looks something like this, where you could have multiple edges between something. Okay, so in simple graphs, if you have O of V vertices, so if you have V vertices, that means that the max number of edges is around v squared. Okay? I'm using the wrong notation there. I'm rusty, right? So just the number of vertices implies that again, I'm a bit rusty. I haven't had to do this for a week. So the number of edges is equal to, I should say the number of edges max is equal to the number of vertices squared. Make sense? In other words, this kind of positioning over here. And you might be thinking to yourself, wait, why that? It is possible for this to exist, where a node has an edge to itself. Okay, I believe I covered that all in the videos, but I just wanted to mention it here. Okay, now a sparse, so this is good. So this is when you want to use an array, a array-based, a 2D array for your graph, an adjacency matrix. You want to use an adjacency matrix, the 2D array, when it's something like this. You want to use on the other hand, for a dense graph, for a sparse graph, you want to do it if it resembles more like this. Okay, if the number of vertices and edges are around the same order of magnitude. The textbook that we use says, rule of thumb, okay, that what is sparse versus what is dense? A graph is dense when 25% of all possible edges exist. Okay, so let's go ahead and look at that. 1,000 node, 12,000. So now with that, where should we use a graph? Okay, this says a graph implementation that uses a two-dimensional array to represent edges would be most reasonable for the following cases. It'd be useful, most reasonable in a case that was dense. So let's start off with D because that's the easiest math, right? There's 10 nodes and 20 edges, all right? 10 nodes, 20 edges. 10 nodes means that there is a possible 100 edges, right? 10 squared, right? If there's 10 nodes, each of those nodes has 10 things it can connect to, including itself. So 20 out of 100 possible edges exist, which is 20%. So that's still that's a sparse graph. Let's go ahead and look for another thing. So if we have 1,000 nodes, then there are 1,000 squared possible edges. Okay, so 1,200 out of 1,000, right? We'll just simply simplify now. So that's 12 out of 10,000, whatever percentage that is. That's a very tiny percentage. This is a very sparse graph. Okay. 100 nodes and 4,000 edges. That's part B. 100 nodes squared is 10,000 edges. That's the max number of edges. We have 4,000 edges total. So simplify the math. Remove 3 zeros on the top and the bottom. That's 4 out of 10. 40% of all possible nodes exist. That means that this is a dense graph because we're looking for something with greater than 25. So yep. And we've already kind of done the math on this one. 10,000 out of 1,000,000, still not that much better. Okay. So the answer for this one is B. Okay. Next question, tree question. A binary tree, not a binary search tree, just a binary tree, is constructed of nodes that are instances of the following class. And so you'll notice that for a lot of classes, they don't necessarily teach generics in how to use Java. And I find that silly. But anyway, a public class node has an int as the key, a left and right, right? We've seen these nodes all over the place. Public static node mystery node root. We have this mystery method, which says that if the right subtree of the root is null, I return the root. Otherwise, call mystery on the rightmost subtree. I consult 3 supposedly tech-savvy consultants, pay an exorbitant amount of money, and I get the following 3 opinions about what the method does when past the reference to the top root node of the binary tree. Consultant number 1 says it returns the last node visited in order. Consultant number 2 says it's the last node visited in post order. And consultant number 3 says it returns the last node visited in level order. Which of these opinions are correct regardless of the concept of the tree? So in other words, which one of these are always true no matter what nonsense tree we make up? Okay, so let's go ahead and just kind of figure out what that does. This method says, okay, we've got a root node. Root.right is, if the right is node, return ourselves. So if the right is null, return ourselves. Otherwise, go to the right. So in any tree that we create, the left subtree actually doesn't matter. All that matters is that we keep going right until we can't go right anymore. That's what that's what this was do. If we pass this node up in, then it will call this node, which will call this node, which will call this node, which will return itself. So this, if I were to express this, this always returns the rightmost node in the tree, or the largest thing in a binary search tree. This isn't a binary search tree, but it's a good way to think about it. So let's go ahead and look at number 1. It returns the last node visited in a in-order traversal. In-order traversal is always process myself, process the left subtree, then process the right subtree. Okay, and each thing does that recursively. That means that we will always process this node down here all the way to the right. That one's going to be the one that's always last in the in-order traversal. So opinion number one is correct. Okay. Post-order traversal. This one's easy to prove that it's not going to be. A post order, right, goes like this. It says I'm gonna process the root first. Sorry, no. Post order says I'm gonna do the left subtree first. Then I'm gonna do the right subtree. So left, then right, then the root. So the root is always processed last. So in a post order traversal, on a nice perfect tree like this is going to be the last node visited by a post order, which is not this node. It's not the rightmost one. So 2 is wrong. Now, level order traversal is, that's just depth first search with extra steps. Level order traversal is basically a fancy way of saying what we do is, I never really go over it because that's all it is breadth first search. It says we do this one, then 2, then 3, then 4, then 5, then 6, then 7. Make sense? That's what level order traversal is. And then if there was another node over here, that would be number 8 over there in terms of being visited. Really want to disable that, like this button over here, the ruler. Okay, so now that seems like it's going to do the same thing. That's always true, but let's go ahead and just simply remove this last node. What happens now? Well, in the case of number 1, it still returns the rightmost node. But number 2, the last node visited by a level order traversal would be this guy. So number 3 is incorrect. So number 1 is the only correct option. With a poorly chosen hash function, it is possible to have a situation in which the search time of a hash table goes to, let's see, search, okay. So if search time of a hash table goes to, so yes, it's possible, yeah, with a poorly chosen hash function. Said I wanted red. I've got to actually hit okay. Here we go. So this deals with collisions. When you have a poorly chosen hash function, you have a lot of collisions. When you have a lot of collisions, that means you have to spend an unoptimal amount of time looking for an empty spot. Now, assuming we're doing what we should be doing, which is we're resolving collisions using open addressing or chaining, then there's no way that this should be happening, or this one. This is what we want to happen, so that's not the answer. And log n, that's what we'd get if we were using a tree. And the answer is A. Right, with a poorly chosen hash function, if you have n items in the array, in the hash table already, it's going to take you O of n time to find that new spot. I'm not going to go over number 6. You've done that one on the exam, number 1. Instead, I'm going to go over this one, which is very good. I like these questions about what are good data structures to use. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets, so it can be very quickly determined whether or not a license plate is in the database. In other words, whether or not a given license plate is a well-known frequent ticketing. Speed of response is very important. Efficient memory of use is also important, but not as important as speed of response. Which of the following data structures would be most appropriate? So this is where so another way to rephrase this is we are looking for the data structure, which would give us the fastest data structure, okay? And if we need to break ties, we're going to break ties with memory usage. Make sense to everybody? So let's look at how long this takes to find something in this. So suppose we have a sorted linked list. That's no bueno. That's going to take O of n time. Okay, sorted linked list takes O of n time to find if a certain item is in it. Why? Just because it's sorted, you don't get to take advantage of what we'll see in number of binary search, like in B, which I'll get into. With A, you have to go with a sorted list, with a linked list, doesn't matter if it's sorted or not. If you want to find if an item's in it, you have to start at the beginning and you have to traverse all the way through it. Okay. So B, the sorted array with 1,800 entries. Now we are getting somewhere. Here we have O of log n. So I'll just do that log base 2 of n, because we can use binary search since it's sorted. Right? We can use binary search since it's sorted. And now this one, if we cared about memory, this would be the winner because it's also, in terms of memory, has exactly no wasted space on it, right? It's an array, no wasted extra space. C, D, and E all are hash tables, which ostensibly, right, if you say hash table, should be constant time. But remember, it's constant time amortized with that big fat asterisk. It's constant time if we have enough space. And the way I like to think about it is that we've got a parking deck, right? So let's go ahead and just think about this. We know we're going to store 1,800 of these things. If we have a parking, and if we have a database of 1,800 items, it's going to take forever to find it. For instance, think about it this way. We have a parking deck with 1,800 spots, and 1,799 of them are full. You know from experience, if you've done any parking decks in that kind of situation, that takes forever to find that last open parking spot. It takes forever. Okay, now 3,600, that's an interesting number. Why is it 3,600? because it's twice 1800. So what about trying to park your car in a deck in a parking deck that is half full? You know the answer to that as well. If it's half full, that means it's half empty. And in this case, half empty is the optimistic thing, right? The half empty is great. That means there's a spot right over there. We'll go and take it, right? So the question is that a marginal difference between that and is that a substantial difference between 3,600 and 10,000, right? Are we going to get even faster with 10,000? And the answer is not really. The way you figure out that the expected number of lookups, right? The expected number of lookups, the expected number of lookups is equal to, into a hash table using open addressing, is equal to 1 plus, and I'm working off of memory here. I think it's 1 plus 1 minus, and let me go ahead and see, yeah, 1 minus, let's see, I think it's 1 minus the load capacity. Yeah, that sounds about right. 1 plus 1 over 1 minus the load capacity. The load capacity, sorry, the load or the load factor. I'll just call it the capacity. In other words, how far, how full you allow it to get. So in other words, if we expect this thing to only get half full, our load capacity would be 1/2. And now we have to do some annoying arithmetic. 1 minus 1/2 is equal to 1/2 over here. So 1 over 1/2 is equal to 2, 1 plus 2, meaning our expected number of lookups for this is 3 lookups. Doesn't matter. And notice it doesn't, that n didn't factor anywhere into that. So it's constant time. For this, let's go ahead and just round, okay? This, okay, the load factor, let's go ahead and round this to 2,000, okay? Because otherwise the math gets annoying. So in other words, that would be, the load factor is going to be 20%, which is 0.2. Sorry, so 2. So 2 over 10, right? So that means that this is going to be 8 over 10, which means that since there's a 1 over it, becomes 1 plus 10 over 8, which is less than 3. It's about 2. Still a constant factor. There's no real difference between doing 2 lookups and 3 lookups, when we get down to it. But we waste a boatload more memory doing E. So the answer is we want to use, and if you're wondering where I pulled that formula from, that's from Donald Knuth. It's from the textbook as well. And I believe I mentioned it in the video lectures. So anyway, our answer is D, because that gives us constant time, and we broke the time with less memory usage. Just double check something, making sure my cats aren't getting outside. One second. Hey, Annie, can you make sure the cats aren't going outside? Oh, Mama's thinking about it. Is Murphy still in here? Yes. Okay.
It's not big enough for them to fit through,
All right.
and too heavy for them to push.
The bag wasn't in front.
You're curious.
All right. So a Huffman tree is constructed for a text document using 5 characters. The character E appears the most frequently, then the character I is the next highest frequency. Which of the following could be the Huffman tree for this document? Okay. So 1, 2, or 3, either 2 or 3 or none of these. All right, so first off, this just isn't a Huffman tree. I can just reject it right out. Why? Because a Huffman tree only has the letters, the symbols, at the roots. Sorry, at the leaves, not the roots. No internal nodes, right? The internal nodes are just for going left, right to figure out the 1s and 0s. Similarly, we can reject 3. Why can we reject 3? It says the most frequent symbol is E, and then the next most frequent character is I. Okay? So, so if they're frequent characters, that means they have the least number of steps. And I and E have 1, 2, 3 bits each assigned to them, as opposed to these guys, which have 2. If E and I are the most frequent, then they should have the least bits. So it's not 3. Next, what about 2? 2 is the answer. It is just 2. 2 is fine. Now, I'll explain why, and I've done this in previous videos, but again, I want to make sure I have plenty of time to go through everything. But we can come up with a symbol tree that would put E here as the most frequent, and the next most frequent is I. And it's ostensible to basically what you have to do is you have to make sure that E appears in order to get it to for this tree to exist like this. What you have to do is you have to make sure the number of times E appears in the document is less than all of these combined, but still appears more than any single one of them. And then also these things have to be roughly equal, and these things have to be roughly equal. So it's a delicate balance, but you can get a Huffman tree like that. An array of 7 integers is being sorted by the heap sort algorithm. After the initial phase of the algorithm constructing the heap, which is the following possible for ordering for the array? I don't think this is on the exam, but it's worthwhile going through. Heap sort, what it does is that it goes through the heapify process, right? It turns an array of unsorted things into a max heap, right? A max heap. I just said max heap, so that means D is out. Why? Because a max heap should have the biggest item at the root. The biggest item in each of these, and you can verify it yourself, you can look at these very quickly. Biggest item is 85, right? And then that's all that matters. That the biggest item is at the top. The rules for heaps are a bit looser than for arrays. For heap, all that matters is that the biggest item is at the top, and that the left side and the right side are both heaps, are both max heaps. And so that's it. It doesn't matter what order things appear in the left side and the right side, so long as on the left side, your left heap, that the biggest item in the left heap is on the left, is at the top of it. Okay. So now the other thing is that any of heap is stored as an array because it's a complete, these are all going to be complete trees, meaning that if we were to write out this in a tree format, 85, 78, 45, it would look something like this. 51, 53, 47, 49. Okay. And that's how that would look. And we can see that this is not a valid max heap, right? A is at the top over here, and that's perfectly great. On the left side, the biggest, whoops. Wow. Whoa. Oh, whoa. That's not what wow. Okay. Wow. There we go. Fine. Not sure what happened there. So we can see that for 45, 70, that for 78, 78 is the biggest thing on the left side. But for 45, that's not the biggest thing on the left side. 49 and 40, it's less than 49 and 47. So if you really wanted to, you could draw the heap for each of one of these, but that's time consuming. There's a formula, if you remember from my videos, that you can go through. But with 7, it's easy enough. 85's children are these 2 characters, and then for 49, its 2 children are these 2, and 78, it's these 2. You can draw it out yourself to verify. So 85, sure, that's bigger. We already know that. So 49 is bigger than these 2. And 78 is bigger than these two. So that seems like a good one. Let's just double check the other ones. Okay, 78 is bigger than these two children. 49 is smaller than these two. And then 85 is the biggest. 51 is smaller than 53. So wrong. So B is our only right answer. All right. Okay. Well, before I continue, since about almost half, I'm a bit more than halfway through the class. Any objections to how quickly I'm going? Or are there any issues with how I'm doing this? And in case you're curious, my plan is to do review on Wednesday as well. And I'm doing the review today and tomorrow. I'm doing the review. I'm doing the review today and on the 24th because I don't know if I'll have the chance to do the review on the 29th because I've been told I have jury duty and I'm trying to see if I can't get deferment on that. So, binary search trees. So now this one I like. This one's, when is the final? We will not be in person on Wednesday. And when is the final? I will, for the final, then that I will send out the email, but I believe the final is on the 2nd because it's a common final. The 2nd, and then if it's a common final, then it'll be at 3:30. I will send out an email. Okay. This is both good and bad. That is that. Do I have time to answer individual questions at the end of today's class? I should have some time, yes. I'm not really going anywhere. Okay. So the binary search tree below was constructed by inserting a sequence of items into an empty tree. Which of the following sequences will not produce this binary search tree? How many points have been lost to over the years to forgetting to read that word? On so many exams. All right. So the way this works is that we just kind of tick through and make sure that this would work. So here's what I mean. Like A, you insert 5, right? That makes sense to be the first one. Makes sense for all of them. Then 3, then 4. So 4 would go to, so 5 is, so 4 is less than 3. 4 is less than 5, greater than 3. So it does make sense to end there, right? Then 9, then we insert 12. Makes sense for it to end there. 7, and then 8, and then 6, and then 20. Those all work. It will make sense once we hit the wrong answer. Let me go from, so, yep, now I'm going to check E. Just see if I can speed this up. 5, 3, so 5, 9, 3, 6. And so C for E, what happened, which is the correct answer for this problem. 5, 3, 9. If we put in 6 next, 5, 3, 5, 9, 3, then 6. 6 would want to go over here, which means that when we put in 7, it would want to go 6, 5, 9, 6, 7, and then we'd get 8. And so we've got a completely different looking tree now. Compared to doing it, and I'll go over D just once more, just to kind of go that. 5, 9, 7, 3, 8, 12, 6, 4, and 20. Okay. Answer 3 of the 4 questions in the space provided. So notice that you'll find this for every data structures in class because of the way individual computer science curriculums are, they go over different things. For instance, this class went over 2, 3 trees. We don't do that in this class. We don't have time for all those trees. But made an emphasis on doing generics because those are actually something in a feature in a lot of programming languages. And this is the appropriate time to introduce them. So suppose the keys on the middle row of a standard keyboard are inserted in succession into an initially empty binary search tree. Draw the tree after those series of insertions. So in other words, A, S, D, D comes before, right? D comes alphabetically after A. D comes before S, right? S comes after, S went to the right because S is after A. F, oh yeah, G, H, J, because they're all in order now, K, L. That is a very, very unbalanced tree. All right. So this question over here, all right, everybody pay attention now, right? This question over here, something like this has appeared on every exam, every final exam that since 2016 for this class. Okay, so and it will look like this. The question will look exactly like this. You are given an empty hash table of size X, right? That uses open addressing, and it's going to be some number that the modular arithmetic isn't so bad to do. The following sequence of keys is to be inserted: A1, A2, A3, A4, A5, A6, A7, whatever. Insert in, and I'll tell you how big the table is. And then then insert the keys using the following approach. So, and we'll typically just tell you to do one thing, which is either, which is most likely open addressing. So open addressing means, of course, that you have basically, or we'll tell you how to do it with chaining. Chaining isn't really that hard though. Okay, so, and you don't have to worry about resizing the hash table. Okay, so let's go this. So we're given with a hash table of size 7 using open addressing. The following sequence of keys is to be inserted: 15, 17, 8, 23, 3, 5. Insert these keys in each of the following approaches. If an overflow occurs, say so, indicate the element that caused the overflow. 15. So 15, where does it go in this table? The hash function is using X is, the hash function is hash of X is equal to X mod 7. So what is 15 mod 7? Well, 14 is the closest multiple of 7. So 15 mod 7 is 15 divided by 7, but what's the remainder? It's 1. So 15 goes into slot 1, right? 15 mod 7 gives us 1. What is 17 mod 7? 17 mod 7, right? We can do that by subtracting 14 from this, which is the closest multiple, or you could just, do your division. But 17 would give us 3. Okay, 8. 8 mod 7 gives us remainder 1. So we would want to put an 8. Uh-oh, we can't put an 8 in number 1. So what we've got a collision. So we need to look for the next available space. With linear probing, that means we're looking for the literal next available space, one by one. So that means here, we're going to go and put 8 over here. We tried to put it into slot 1. We couldn't, so we put it into slot 2 instead because that was open. Let's look at 23 now. 23 mod 7 is 2, right? Because the closest thing is 21. 23 minus 21, we get 2. So 20, so we want to put it over here, and again, there's a collision. So we try to go to the next available space. There's another collision. So we try to go to the next available space. And guess what? We found an open space now, 23. 3 mod 7, if it's less than 7, the math is easy. So 3 mod 7 tries to go over here. We can't put 3 into here. We can't put 3 into here. So instead, I'm putting it over here. Doesn't have to be how you indicate how collisions occurs. I just find it useful to do it like this, or rather easy for me to draw like this. And then trying to put 5 into here. 5 tries to go in that spot, and you can't. Okay. So common question we get, all right, is what if, common question one you should definitely know the answer to is, suppose we're in this situation where we have we have something like, let's see, we have 13 over here, right? We put 13 in here, and the next thing I want to insert is, so suppose we have this, and the sequence is instead 13, and then what else would go there? 13 and 20. So do you want to put, so suppose our sequence would look like this, 13, 20, right? So 13 mod 7 is 6. 20 mod 7 is 6, but we can't put it in there. So what happens? Well, you look for the next available space, which means you go all the way around. To the beginning. Make sense? Okay, so now we're going to do the same thing, but rather than doing linear probing, we're going to do quadratic probing, which means that we look for the next available space, but the next available space, well, first we look 1 away, then we look 4 squares away from our initial position, then we look 9 squares away from our initial position. Okay, rather than looking 1 away from our initial position, then looking 2 away from our initial position, then looking 3 away from our initial position, right? Okay, so you're not looking at 1, then 5 away, you're then 14 away. You're looking at 1, then 4, then 9. Not 2 to the 9th, that would be 3 to the 9th. That would be rather extraordinarily big. Okay, so quadratic probing has the advantage of spacing things more out, but you got to do another additional math operation to compute that. Got a multiplication operation thrown in there additionally, in terms of the computer's efficiency. But honestly, it's fine. Okay, so this starts out the same. 15 ends up going to spot 1, right? 17 ends up going to spot 3, right? 15 minus 14 is 1. 17 minus 14 is 3. Then we've got 8. 8 wants to go into here, just like we did last time. 8 mod 7 is 1. So we try to put it in there. We can't. We go to the next. We look 1 squared away, which is 1 space. Okay. And so we found a space. We put it here. Okay. Next, we try to put in 23. As we remember, 23 minus 21, or 23 mod 7, is going to be 2. Okay, so we try to put 23 here. We cannot. So we look 1 away. We can't put it there. So we looked 1 away from our initial spot. Now we're going to look a grand total of 4 away from our spot. So we're going to go, so we were looking at 2. Now we're going to look at 6. And we'll go ahead and put 23 there. 2, 1, 2, 3, 4. Yeah. Now we try. Now we put we try to put 3 in over here. We can't, so we put it in 4. But when we get to 5, we can just directly insert 5 because that space is open. Double hashing, we're not going to worry about that because I didn't cover it. Basically, instead of this case, what we do is that here we look for the next available space if we have a collision. Here we look for the next available space where we define next differently. Here, double hashing means we have hash function number 1, and now we have hash function backup to, we have hash function number 2 as a backup. Okay. Oh. Do I have time? Yeah, okay, I already answered that. Okay, graph algorithms. So this again will definitely be on the exam. On the exam, typically we don't give you, on the exam though, we typically don't give you this. Instead, we give you that adjacency matrix or that adjacency list that we told you, that I mentioned earlier, one of the two, and then ask you to reconstruct the graph from there. Okay. So lots of paper, in other words. All right. Well, we don't directly, we just simply, we don't give you the graph, we give you the matrix or the list, and then we tell you to do depth first search on the graph or breadth first search, one of these two. So let's practice by doing one of these two. Can I erase these? Yes, I can. Cool. All right. So depth first search works like this. It says, perform a depth first search starting with vertex C. Select the smallest edge first when appropriate. In the space below, list the vertices in the order that they are visited. So C, and here it's saying, right, with depth first search and breadth first search, it's you got to have a way of breaking ties, right? You have to have a strategy on an exam, right? In real life, you could just simply flip a coin and say, I want to randomly choose this one. In the exam, we need a way to get consistent answers from all of our students. So in this case, we're saying on our exam, typically we'll tell you to break ties alphabetically. On this exam, it works out to the same thing. It's asking you to basically choose, if we're starting at C, right? We have B, E, and F to go to, and we'll figure out which one to go through, which has the smallest weight. C to B is 5, C to E is 22, C to F is 30. This one has the smallest weight, so we'll go and travel to B first. So depth first, so let's go ahead and just write this down. We went to C, and then we go to B. And then I'll keep track of where I am, right? I'll keep track of where I am, of what I've already seen. So I can keep track of where I am with a stack. C and B. And then I can keep track of where I've been or what I've already seen, so I don't repeat seeing anything with a set, right? If I didn't keep track of where I've been, if I wasn't circling where I'd been like I have been doing, then the issue becomes, geez, why is this happening? I don't know why that is happening. That is very frustrating. Never, I think Google made an Edge made an update, wasn't trying to be useful. If you don't pass a set in, then you get into an issue where like, oh, B, I haven't been to C yet. Oh, C, I haven't been to B yet. So you want to keep track of where you've been. So anyway, C, then B, then what we need to do is we go from C to B, we go, okay, we've got 18, 20, 13. So we're going to go to A next because that's the smallest. A says we are going to go to D next because I've only got 2 neighbors. B I've already been to. I haven't been to D yet. So there's no ties to break. And D basically says, okay, you're at a dead end because I can't visit any of my neighbors. So pop the stack. Okay, so we go back to A. We pop the stack. We go back to B. We don't pop at B because guess what? We have other neighbors to visit. We have E and F. E is 20, F is 18. So we go to over here next. And then B to E, we go over here next. So C bad fee. I'll leave Dijkstra's for a separate exam on a separate set of problems because honestly, doing Dijkstra's on this particular example isn't very useful. I've done it before. You can do it. You can do it on any graph. It's just not useful for this one. So I'll go over breadth first search to make sure we know how to do that one. Okay, where is that thing now? There it is. There we go. Okay, so breadth first search, traversal. So start at C, and now do break ties alphabetically. This is even easier. It says breadth first, so I'm just gonna scratch that out here so I can don't have to scroll. So C, we start at C, and then we go to B, and then we go to E, and then F. And basically, we'd load this up in a queue, right? What we would do is we'd say, technically what we do is we say, okay, I've got a queue here. C's in the queue, okay? It's the only thing in the queue. So I get rid of C, I visit C, and I'm gonna add B to the queue, E to the queue, and F to the queue because those are C's neighbors, right? And I want to visit them in the order in which they've been, which they're the cheapest to visit, 5, 22, and 30. So that's our key. So we're done with C. Now we visit B because that was next in the queue. B says I've got to add B's neighbors. E and F are already added. A and D. So here, whereas depth first search, for depth first search, you care if you visited it, okay? But for breadth first search, it's more caring if you've seen it. Oh my God. Well, we've already got the answer. It's CBEF AD. Okay. CBEF, because we'd go through all of our neighbors, all of C's neighbors first, then we would finally do the ones that B added. Okay. Prim's algorithm and Kruskal's algorithm. Prim's, which one is that? Doesn't matter because that's not this class. That's 3223 where we go over it. Prim's and Kruskal's are greedy algorithms that are taught in 3223 that generate a minimum spanning tree. And I can't remember which is Prim's and which is Kruskal's. But I remember how to do both of them, just not which is which. They're both very easy though. All right, so let's go ahead and get started. We have about 15 minutes left to do some programming. Okay. Complete all. Suppose that this Java method uses recursion to search for a key in a binary search tree. Okay, so right, we've seen this before, just with generics. In the space below, rewrite it so it doesn't use recursion. It uses iteration instead. All right, let's go ahead and do that. So instead, we're going to do, instead of doing search for a key, the contains method or whatever, we're instead going to do, we're going to instead do EST. We're going to instead do search with a, with iterative. So ESTE extends comparable B. There we go. And then we have a node, sorry, private class node E item, private class node E extends E. I'm not sure if I have to do it like that. Forget. Private class node, and what we've got over here is we've got E item, node E root, sorry, node E left, node E right. There we go. So I probably don't need this, I bet. No, do I? Oh, looks like I do. Okay, great. Now, let's go ahead and we've got and really all I need here is just, I don't even really need to put this in, but public node e root. That's one of the fun things about Java. I can use it before I define it because it's smart and of the way it compiles stuff. Cool. Okay. Public static. They're public. Let's return. What did it want me to return? It wanted me to return the object, right? Because it had this whole, oh, it has a key and a data. Whatever. Doesn't really matter to me. Let's just go ahead and look for the item that's being stored. The key and data, honestly, that's not the important part of this. Public e search. In that case, we'll just do, does it have it? Boolean search for e item. So we want to do this iteratively rather than, so we want to do this iteratively rather than recursively. So we start at the root. So we say node e current equal to the root. And this is actually fairly straightforward. I'm not even going to bother. I'm just going to write it out because I want to make sure I get to the next problem, which is a fun one that we've actually asked on the final exam before. While current is not equal to null. While current is not equal to null, if item is less than current dot item, sorry, if current dot compares to item is less than 0, current is equal to current dot left else if it's greater than 0, current dot right. And then if it's not less than and it's not greater than, then that means it has to be equal to, so return true. We found it. Great. And then by default, if we can't find it, we'll just simply, if we end this, that's because we hit null, which means it doesn't exist. So return false. Boom, done. Okay. Yeah. All right. So again, we've actually asked this one on the final exam before. So write a Java method called mirror that takes a reference to the root node of a binary tree, so this guy, and creates a new tree with its own nodes that is a mirror image of the original tree. For example, if we pass in this tree over here, then we want to return this tree. So notice that basically that one has children's 2 and 3, but 2 and 3 are swapped, and also 2 and 3's children are swapped, right? 3 has no children, but 2, 5 and 4, 4 and 5 versus, and 5 and 4 over here, and then 5 has the same children, but it swapped them. 6 and 7 versus 7 and 6. Everybody following that? So this looks like a tough problem, right? And I admit it very much does look like a tough problem. And probably the only reason it's easy for me is that I've went through this problem a lot. But again, where do we start with? Base cases. That is where we start with, okay? So what's a good base case for public static, not public static, but the method called mirror. What is it going to return? What should this thing even return? It should return, right? It should return a node. because it's going to be the root of this reverse tree or subtree. Public static mirror. And let's just go ahead and do it the weird way that I like to do it. Just to remind you, you can write more than one method. Okay, mirror root. Right? And the important reason for this is when I do it this way is to remind you that whenever we're dealing with a recursive recursion method, we don't just start, yeah, we start at the root, but when you're problem solving, you don't actually know where you are. You're at the root of some tree, which could be the root tree of the entire tree, or it could be the root of a subtree. So we're here at this node. Okay, so let's think through base case. If root equals null, then, well, if I don't exist, then neither should me in the mirror image, right? Oh, this shouldn't be void. This should be node. It's the same. And this should return mirror. Next. Okay, if I do exist, well, honestly, the mirror of myself, I don't really care about. So if I don't have kids, that's easy. If I exist, but I don't have kids, I just return myself. So, except I don't return myself, I return a copy of myself, right? It's a copy, creates a new tree with its own nodes. So let's see. If I do exist, well, I got to make a copy of myself, right? And that's what I'll return. So, so node E, my clone, is equal to new node root dot item, right? Gonna give it, it's the same node. So it's a new node with itself. And regardless of however my children are, right? If whether my children exist or not, I got to return myself. That just leaves my children. Now, honestly, figuring out the left subtree and the right subtree, well, figuring out how my left subtree and a right subtree, how they're supposed to create mirror images of themselves, that's their own problem. But for me, all I know is that for me, locally, if I've got a left subtree, then it's going to be my right subtree. And if I've got a right subtree, it's going to be my left subtree. So my clone dot left is going to be equal to the mirror image of root dot right, and my clone dot right is going to be equal to a mirror image of the left. And let's just think that through. Okay, if they don't exist, I'll get null back, which is perfectly fine. And if they do exist, they'll figure out how to mirror themselves. And as part of doing that, what they do is they make a clone of themselves, and then I can just simply attach it over here, right? Same over here, attach it over here, and then I return myself. And that's actually the entire problem. This is it. That is all that function is, to do that. Right, let's go through from the top. Given the root of the tree or subtree, if it doesn't exist, well, the mirror image of it is nothing. If I do exist, the mirror image does exist. Then, sorry, if I do exist, then I need to make a copy. So I clone myself and make a new copy of myself. Then I get the mirror image of my right subtree to put on my left, on the clone's left. Then I get the mirror image of my left subtree to put on my right. Right? 2 will copy itself and do the whole mirror thing on its children. And 3 will do a copy of itself, mirror image of its own children. What is the runtime of this algorithm? O of n. Almost everything from a tree, it's either n, it's either n log n or just log n. It's n here because what we do, every single node in the tree, we just simply visit it once. That's it. I clone myself, then I tell my children to clone themselves. I don't do any extra work beyond that. Okay. So I've went over this. I will have even more practice problems for us on Thursday. Okay. So, and again, I'm just trying to make sure that I'm going through these quickly so you can, and I'm recording it so you can review this. I just want to make sure that, that the final exam is going to be as stress-free for you as possible. All right. All right, stop recording, stop sharing. All right, class is dismissed. If you need to talk to me, I'll stay behind.